All right, so last lesson of the year, last chemistry most of you will ever take. It's going to be on gas laws, something called thermochemistry. So first we're going to start off with the gas laws, and you're going to see these abbreviations, PV, T, and pressure, volume, temperature, later N, number of moles. So I want you to rationally think through these here. For example, if we have a closed container, and that's what these gas laws are about, and the temperature, we're to heat it, and the volume couldn't get any bigger, what would happen to the pressure inside the container? And get some of these that are conceptual thinking. A good way to test this, your theories, is to go to this link and see what happens. You can make one thing stable and play with the volume, the temperature, and the pressure. So normally when you learn the gas laws, you learn about Boyle's law, Charles' law, Gay-Lussac's law, and so forth. But the way that I like to teach it is just one law. It's called the combined gas law. So you don't have to know these names. But essentially, it's P1 V1 over T1 equals P2 V2 over T2. And then if a variable is not used, or if it remains constant, then you just eliminate it. So if pressure remains constant or it's not mentioned, we just get rid of it. Now, volumes in liters. Temperature is always going to be in Kelvin, and we'll just do 273 here. These are just different pressures, and you're not going to get all these pressures in your work. Well, you might, but you're not going to have to convert between these. And they're just different ways to measure pressure. Where an ATM, a 760 torr, is 760 millimeters of mercury, is 101.3 kPa, and those are just things you're going to hear. And all those are pressures. So let's try some combined gas laws, or let's try some gas law questions here. And I'm just going to write P1 V1 over T1 equals P2 V2 over T2. And we're going to read this question. It wants to know the new volume. It says 22.5 liters of nitrogen at 700. So we have a liter there. So we got V1, 22.5 liters at 748 mmHg. So we talked about before, that is just a pressure, 748 mmHg is compressed to, so here it doesn't mention temperature, so we can get rid of temperature. It's compressed to 725 mmHg. So P2 means pressure final, and 725 mmHg at a constant temperature. So that's another way we can eliminate temperature. What is the new volume? So essentially 748 times 22.5 equals, so I'm just plugging those in here. P1 V1 equals P2 V2, 725, and we want to know the new volume. So again, we're eliminating temperature. We have an initial and final. Sometimes you'll see teachers write initial, volume initial, pressure final, volume final. So 1 is essentially there. So this is 748 times 22.5 divided by 725. And we know that since the, so what's going down? The pressure is going down, so the volume has to be going up. And so volume 2, and whether or not that makes sense or not, you just plug stuff in. So volume 2 is going to be 23.2 liters. Another one here, and I'm just going to start off with P1 V1 over T1 equals P2 V2 over T2, and calculate the decrease in temperature in 6 liters. So we got volume 1, temperature 1, so we have to convert that to Kelvin. Now, the reason for that is we could have a negative temperature, and you're not going to have a negative volume. So essentially, everything has to be converted to volume 1 but 6.00 liters. It's compressed to 4 liters. Volume 2, 4.00 liters. So something here is not being used. It's not going to be true all the time. You're going to see in the next one. But so what we got, volume, and we got temperature. So pressure is not mentioned anywhere. And now we can just do V1, 6.00 over T1, 293 equals V2, which is 4, and we want to know the decrease in temperature, T2. So to solve this, here we can cross multiply and divide, or whatever works for you. 4.00 times 293 divided by 6, and T2 is, and we have 3 sig figs, 3 sig figs, 3 sig figs. T2 is going to be 195 K. Now keep in mind, it says, you got to read this carefully, what is a decrease in temperature? So it starts off at 293 and it goes down to 195. So the decrease in temperature is going to be 98 Kelvin. And Kelvin does not have a degree on it. All right, so another gas law, P1 V1 over T1. So you're going to use this gas law whenever something is changing. A gas balloon has a volume of 106 liters, so volume 106.0. The temperature is 45, so T1 45.0 plus 273, and that is 318 K. P1 V1 T1. I'm just reading through this. Okay. The pressure is 740 mmHg. P1 740.0. What is the volume? What will the volume be at 20 degrees Celsius? So now we got a T2. So 20 plus 273 is 293. And 780. So we got P2. So we're going to use all these variables because there's only one thing missing here. And we want to know what is the new volume. So we got to plug all these in. So 740 P1 V1 06 over T1 318 equals P2 780 V2. And so that's what we do not know. Over T2, 293. All right, so solve for one side, 740 times 106, and you can solve this however you want, obviously. So 318 times 293 divided by 780. And so volume 2 is, we got, let's look at the question. Everything looks like 4 sig figs. Nope, we got 3 sig figs right there. And so it's going to be 92.7. And we are looking for volume. And so that's going to be liters, because the question itself right there is in liters. And so here's a bunch of example problems that I'll solve, I guess. It's just, I'll solve and give you the answers. So now, this is something that you're going to learn. I hear physics students talk about this equation all the time. Now, when we did P1, V1, T1, this P2, V2 over T2, there's a change in the system, like volume's changing, or pressure's changing, or both, or temperature is changing, or whatever. But if it's an idle system, meaning there's no change, we use PV equals nRT. And pressure, volume, N is number of moles, R is going to be a standard that we're going to see, and T is in temperature. So I have a bunch here with the answers. Unfortunately, the sig figs are off. And anyways, we have a system here, and notice how nothing's changing. We use this R, 0.0821, when it is in ATM, when pressure is in ATM. We use 8.31 when it's in kPa. And so I'm just going to write PV equals nRT. This isn't going to be too tough because I'm just introducing it to you. Volume, we got 12 liters. Moles, we got 4. Pressure, we got 5.6. And what is its temperature? We do not know. And since pressure is in ATM, we're going to use 0.0821. So we have to find the temperature here. And so we have 5.6 times 12 divided by 4 divided by 0.0821. And I got that same answer there. If I went back to the question, though, we only have 1 sig fig there. So let's just pretend that's 2 sig figs. Moles. Well, that's going to make it harder, because that's going to make it, that's going to be tough. It's going to have to be 2.0 times 10 to the second. And we're always going to have units on these, and that's Kelvin. So let's try one more, and all these here have answers on them. Here we're going to have 2 sig figs. Remember, Celsius is fake, so you always have to add 273. And so I got PV, so 1.2, pressure, volume, 31, equals N. We don't know what moles are. R, since pressure is in ATM, R is 0.0821. And then T is 87 plus 273. And so now we can solve for So 87 plus 273 is 360. Now we can solve for n because it wants to know the number of moles. 360 times 2.0821 divided by 1.2 divided by 31. And I got 1.26. We go back to the question, we got 2 sig figs, 2 sig figs, 2 sig figs. So this should be 1.3 moles. And so all these need to have an answer or have a unit. If it's n, it's moles. And really, I mean, it sort of tells you in the question what the unit is going to be. And here's just a bunch more practice ones, but you know, I wish that the sig figs were right because this would be 1 sig fig. This would be 1 sig fig as well. This would be 2. So they have that right. This will be 1. So that's right. This will be 2 because we go with the least amount. So that's going to be tough times 10 to the first liters. 2, 1. I should have picked a better worksheet. It's too late now. It's Monday night at 10. So, and so you can practice these. Make sure you get here for this one. So there, if you pick 0.0821, sorry, 0.0821 for R, you're going to get this. And if you pick 8.314, you're going to get this for the R value. And I guess either one is fine, I guess, yeah. All right, just more practice ones. All right, so now one last thing. The last thing you're going to learn is thermochemistry. And we're essentially just going to look at this one equation. What your lab is. Next week, your lab is gas laws. This week, it's Q equals MC changing T. You're going to have a formal lab, but it's going to be much more simpler and straightforward. So I don't cause too much stress. And well, anyways, whatever. So we have this Q, MC changing T. And keep in mind, whatever you're going to see, you can essentially solve with this. Where Q is in joules, it's energy. M is mass in grams. C is something called specific heat. Specific heat or heat capacity. Alex calls it specific heat capacity, which is good. But you might just see one of the two. And delta T is essentially T final minus T initial. That's always what a delta means, is change in T. And so what is heat capacity? So it's essentially the energy you need to weigh to raise 1 gram of something. So the joules needed to raise 1 gram of something, 1 degree Celsius. So think of the sun, and let's say if, you know, the car's out in the sun is releasing energy, and the hood of the car will feel hot because the energy is raising that 1 degree Celsius. So you're going to see a lot of different specific heats or specific heat capacity. I should wrote specific heat capacity there. And we're going to do some practice problems with that. So what are some things that have a high or low heat capacity? So think of water. Water is one of the most famous ones with a high heat capacity. So water ends up being 4.18, the heat capacity of joules per gram degree Celsius. That's really high, meaning if you have water out in the sun compared to, I don't know, a penny, and they're in a bucket or whatever, and the sun is shining down, water, the penny is going to feel way hotter. Or if you had an equal amount of grams of pennies to water, the penny is going to feel way hotter than the water because copper has a lower heat capacity. So things that have low heat capacity are metals. If you have a metal out in the sun, you touch it on a hot day and it feels hot. Something like aluminum has a higher heat capacity. Like if you put an aluminum can outside in the sun and you touch it, you're not like scared to touch it compared to, the top of a car like iron. And so essentially how fast it would raise the temperature 1 degree Celsius, or how fast would it take to make something hot. So I'm just going to tell you how this relates to water, and all this is based on water. And the specific heat, so if we did Q equals MC, change in T, and let's say we have 1 gram of water, the specific heat is 4.18 for water. You're going to hear that in your career here. And let's say the change of temperature and is just 1 degree Celsius. So Q ends up being 4.18 joules, which raises 1 gram of H2O up 1 degree Celsius, which is also equal to 1 calorie. So a calorie is defined as 4.18 joules, or the energy it takes to raise our body 1 gram of the water in our body 1 degree Celsius. And like the average person's temperature, this is 98.6, lower now because they're not actually sure, but they think because of people are getting less sick due to better health and all that. So it's like 97.8, but it's still somewhat of a mystery, the average person's temperature. But anyways, if you lay around all day, you can still burn, I forgot what it is, but like 800 calories a day if you don't do anything. So, like what I plan to do over winter break is lay around, and if I eat 800 calories a day, I'm not going to put on any weight. So that is how this relates to water. So you have 2 ALEKS modules due, and we're going to do, both of them are Q equals MC change in T. So if you see this calculating specific heat capacity, and it gives you the units. So earlier I wrote, we'll see how K is the same thing as 1 degree Celsius, because if you go up 1 degree Celsius, you go up 1 Kelvin. So it doesn't matter, but they give you the units. So earlier I said, joules per gram degree Celsius. That's not something you have to memorize. But anyways, for both the ALEKS that you have due and that will be tested, it uses just that same equation Q equals M. Some students say Q equals MCAT. And we're just going to plug stuff in where we know Q is in joules. Sort of looks like a J. I don't know if I'm alone with that, but M, mass, grams. Change in T is temperature final minus temperature initial. And this is C is specific heat capacity. And that's what we're finding here. So we can just essentially look in the question. It has a whole bunch of words here, but it's not, I just, I have no idea what it's saying, and we'll be able to solve it. Because here we got kilojoules. We have to convert that to joules. We're going to move the decimal 3 times. So that's 85200 joules. Goes mass, so we're going to look for a gram. We have kilograms there, so I'm going to move that 3 times because we want to convert it to grams. Specific heat is what we're solving for, and change in T is this minus that. You can convert that to Kelvin if you want, but you don't have to, because remember, 1 degree Celsius equals 1 degree Kelvin. Sometimes in my teaching career, I've had them convert it to Kelvin just because they're used to it, and I want them, on standardized tests to do that, but you don't really have to. So here, that's going to be, you're going to find the same difference. If you added 273 to both of those, it's going to be the same difference. So 68, what is that, 12.2 degrees Celsius. So we got to find specific heat here. Q equals MC, so C should be in there. And we're going to go 85200 divided by 1670 divided by 12.2. And so this is water. It's sort of a trick question, I guess, because it ends up being 4.18 joules per gram Kelvin. But those units are there, which is what we said water was. So it doesn't say anywhere in the question that it's water, but whatever, we solved it, and that's all you need to know. You don't have to memorize 4.18. And then another one that you have do it is using specific heat capacity to find heat. So you got Q goes M, C, change in T. Remember, Q is J, M is grams. This is change in temp, and this is specific heat capacity. So some students would say, I've had like, oh, the weird units one goes where C is, and that works. And here we have to find heat, which is joules. So heat and energy are correlated. So we're just going to read the problem, or not even read the problem. We could just plug it in. We got Q equals 1.30 kilograms. We want to convert that to grams. So we're going to move that decimal 3 times or multiply by 1,000. Q equals MC. So this is 4.18. So I don't know if they do this for all of them, but it's water again. And then change in T, and 47.8 minus 25.1, what is it, 22.7. And we can then solve this. 1300 times 4.18 times 22.7. And we get a pretty big number, which sounds about right. I was doing these quite a bit today with students, and Q, we end up with 1, 2, 3. We want to go with the right amount of sig figs. Let's go back to the original question. 3 sig figs, 3 sig figs, 3 sig figs. And so then we get 1, 2, 3, 0, 0, 0 joules. Now, Alex might make you put that in scientific notation, but they both have 3 sig figs. And just remember, Q is joules, M is grams, specific heat is a weird one essentially, but you don't have to memorize those units. And change in T, either Celsius or Kelvin. So, well, that's the last chemistry we got to learn, and I hope you're happy, because that's all. That's it. All right, bye.